Well, welcome and good morning to yet another CppCon 2016 talk about performance, why it matters, and how to get it. Specifically, I'm going to be looking at a slightly different aspect. For example, in many years past, there have been a lot of talks about compilers and how their optimizers work to transform your code to make it run faster, but no one has ever really talked about how to get the compiler to make these optimizations happen. So that's what I'm going to talk about today. In particular, from my experience in doing scientific computing in astronomy. Yes. So I'm a fourth-year PhD candidate in astronomy at UW-Madison, but my background is actually in computer science and physics. So that's really where I like to sit, is in the medium between computing and science. So originally, my talk was going to be called Learn You a Compiler Switch for Great Good, but the abstract committee requested that I change the title. Has anyone read this book or have heard of it? Okay. So its author claims that its purpose is to demystify functional programming for the everyday person. My hope is to demystify compiler switches for the everyday person. So let me talk a little bit about scientific computing so you know where I'm coming from. It's a little bit different than desktop computing. So it's really just the application of high-performance computing to solve scientific problems. That's it. Today's computing standard is in the petaflop range. It's 10 to the 15 floating point operations per second. This is usually done on systems with at least tens of thousands of cores. Some of them have millions of cores. And more accelerators are being used every year. And in fact, this is where I'm specializing, is using things like GPUs, Intel Phi, things like that, the many core systems. And performance in these systems matters enormously because you can be using months of computing time, of actual wall time, not CPU time. That's easy, right? 10,000 cores an hour, and you have months of wall time, or CPU time. But I'm talking about months of wall time to run your problems. So performance matters enormously. Gains of percent level changes can get you a lot of cut down in time. So you had a question? The clock on the wall, yeah. So of course, excuse me, we have to talk about Knuth, right? He says, beware, beware of that last 3%, right? Don't spend all your time in there. Well, scientific computing is a little bit different. It's more like an 80-20 split, where 20% of the code is what matters, not the last 3%. And 90% of your runtime is spent in 20% of that code. So premature optimization doesn't really hold as much. You have to always be thinking about performance in HPC and scientific computing. Here are some examples. These are the top 5 of the top 500 supercomputers from 2015, 2016, whatever the most recent list is. And the number 1 is, well, the first 2 are in China, but the number 1 has 10 million CPU, 10 million cores. Most of these are actually PHYs, with 125 petaflops of compute performance. And we're consuming about 15 megawatts of power. Now, the DOE wants to move us into the exascale from 10 to the 15 to 10 to the 18 flops. And in 2012, they said, oh, you know what? We can't actually do that right now because there's a massive power issue. Because if we want to take the number 1 supercomputer today, we need to multiply this number by a factor of 8 to get to the exaflop range. But if you multiply that number by a factor of 8, you need enough power to power the entire city of Bellevue for 1 supercomputer. This is a massive issue. So how are we going to fix this? Well, the density of computing has to go up, and it has. The multicore world has turned into the many-core world, and that's giving us a leg up. Because you'll notice that the compute between the number 2 and the number 1 is about a factor of 3 in the number of cores, and about a factor of 2.5 in the amount of flops, but the power consumption has gone down. So the flops per watt are getting better, but so to do that, we need lots and lots of cores, And accelerators are where we're at right now. The next generation of CPUs are bringing 28 and 32 cores per socket, really per chip, right? So if you start throwing a few of these into a single node on an HPC cluster, you're going to be talking about 128 cores possibly. With now SMT on AMD and hyperthreading on Intel, you're talking about 256 simultaneous hardware threads in a single node. That's without any accelerators, right? So these numbers of CPU cores are actually going to be matching, number of CPU hardware threads here are essentially matching the number of physical cores in today's accelerators. Excuse me. So making better utilization of these machines is imperative, right? We need to make sure that we're using the hardware that's there because we can't keep making them bigger and bigger and bigger. We can't expand our supercomputing centers by a factor of 8. We don't have enough power. So we have to make sure that as the density of computing cores goes up, we're actually using all of these cores. And of course, this extends well beyond scientific computing, right? You just need to look at the WG14 group, the impressive attendance at this year's low latency class, right? All of this stuff matters. Soon, the desktop is going to have 16 cores. Not a problem. My 4-year-old machine has 8. So this is coming to a hardware near you. But there is a lot of existing software today, a lot. So how are we going to get this software to run better on these new enormous core machines? The first option is to rewrite the old software. And that's what we do a lot of times, right? The C++ 11 and 14 standards brought us some fantastic multi-threading stuff, so we can rewrite our software. The other is to instruct the compiler to make better code. And of course, these two things are not mutually exclusive. And today I'm going to focus on the latter section. Okay, so dragons. Compilers are always represented by dragons for some interesting reason. And as we'll see, that's kind of an apt name for them. But I'm going to be focusing on the interface here between our beautiful code and these dragons. What comes out is what it is, but we're going to be focusing on this interface here. Like I said, there were lots of lovely talks from previous conferences to discuss how these dragons work and to watch out for them. And I'm going to talk about how to get your code how to get these dragons to deal with your code in a better way. So to do this, the compiler needs to know a few things. It needs to know what the allowed transformations of your code are. It needs to know your target architecture. This is actually quite important, as we'll see, but it's also really hard to do in a generic way. And of course, any space-time trade-offs that you want to make. Folks familiar with optimization flags know all about the space-time trade-offs. And so to do this, we're going to use lots of compiler switches. And so just a quick quiz, show of hands, how many switches does GCC 6.2 support? How many here think it's more than 100? Okay, more than 500? More than 1,000? When I counted, it was 2,257. Okay. Obviously, not all of these are relevant to you at all times. But compilers are enormously complex devices, and they offer lots and lots and lots of switches. Okay, so I categorize switches in 3 very broad, totally made-up categories. The first one is compile time static analysis. This is your warning flags and friends. You are using these, aren't you? Profiling and analysis, PGO, with gprof and gconv, and of course the wonderful sanitizer flags that were brought to us by Clang. And lastly is code generation. So these are your O flags for optimization, your architecture flags. We're going to talk about fast math as well. I do apologize if that makes some folks uneasy. And LTO, also known as link time optimization or whole program optimization. This is some fantastic stuff. It's still not entirely ready for complete production, but the LTO that's offered in today's compilers is pretty good. The problem is that it's very complicated, and I don't have time to talk about it in detail. You could give a whole 2-hour lecture on LTO today. Lots of interesting things can happen there. Okay, so is using O3 going to be okay? There's a lot of mythos surrounding O3 on compilers. And so there are actually some reasons not to use O3. For example, if you have written terrible code where the correctness relies upon undefined behavior, probably don't want to use O3. For example, if you're breaking the aliasing rules. Of course, that won't work at O2 either, because all the compilers do strict aliasing at O2. So, and if you don't have unit coverage or load tests, although that or should really be an and, then don't start messing with your compiler flags. Because if you don't have a way of measuring the correctness of any changes that you make or performance changes, then you have no idea whether or not you've done good things or bad things. So testing, if you don't have a full-fledged testing suite, don't start messing with this stuff. Start there first and then come back to this. And of course, FUD, fear, uncertainty, and doubt. There is, I just went Google searching for this the other day, and there were posts as of this spring where people were like, oh, O3 is evil, don't ever use it. The space-time trade-offs aren't worth it. Just put O2 in and everything will be fine. Yeah, hopefully you'll walk out of this talk knowing that that's not true. And in particular in scientific computing, because scientific computing dates back to Fortran 2, Fortran 77 is very popular. There's a lot of very bad ideas about what can happen if you turn on these hard optimizers, because some of that stems from folks who were around in 1977 when that came out, and they've seen how some of these compiler flags have done bad things in the past. Yes, compilers are software, they have bugs, beware of that, but today's compilers are actually really, really good. It's fairly infrequent that you find a really hard optimization bug. Of course, there's missed opportunities for optimization all the time, but those are enhancements, not bugs. Well, Chandler might say they're bugs. It depends. Okay, so we'll look at two particular ideas in that turning on higher levels of optimization are going to cause errors in your calculations, which we worry about a lot in scientific computing. If you're tracking a moon around a planet, you don't want that moon to suddenly crash into the planet. That would be bad. And code bloat is another one that we worry about. A little bit less in HPC because we don't care about the binary size, but some folks get very concerned about that, and rightfully so. So let's look at this. To do this, we're going to do a little simple test case of a reduction operation. Do recall that floating point arithmetic is not associative. That is, if you add x to the quantity y plus z, it is not guaranteed to equal the quantity x plus y plus z. And John Ferrier had an excellent talk last year at CppCon on this, and I strongly recommend if you need a refresher on your floating point properties to go watch that video. And in today's hardware architecture, so at the hardware level, this means that instruction level parallelism like SIMD and out of order execution can affect the result, because you're allowing the x plus z to be calculated before the x plus y plus z, or any permutation thereof. And if it's not an associative operation, it will change the answer, possibly. And I'm testing 10,000 single precision floats uniformly generated in the range of 0.1 to 0.9. Does anyone know why I chose that range? Yes, it's where the most precision is. And if that surprises you, go see John's talk. I'm testing 3 industry standard compilers, GCC 6.2, Clang 3.9, and Intel 17. These are all less than 2 months old now. Sorry, VC does not exist in my world. If you want to try this out on VC, I'll have the code available on GitHub. Although interestingly, Clang doesn't exist in my world either, but I hope to change that with this talk. And I use 2 different algorithms for doing this reduction operation, stood accumulate and operator bracket on T star. We're going to test 4 different optimization levels and no other flags. So this is just changing 1 flag at a time on different compilers. All right, so here's what it looks like. So the sum that it's getting is 5002.66, and then the 3rd decimal place is changing. Okay. So already we're looking at, if you normalize this, the 6th decimal place. Does anyone know roughly the machine epsilon for single precision floating point arithmetic? It's about 2 times 10 to the negative 7 on my machine. So we're not at machine epsilon, but we're pretty close. All right, so the first thing to notice here is that my two different algorithms are represented by X and star. So the algorithm that you use, for example, in GCC, can have more of an effect than the compiler optimization flag that you're using. And red is 0 and yellow is 03. And notice that they're all stacked on top of each other here. I actually had to separate them out so you could see them. So there's actually no difference in the answer between 0 and 03 here. There is for 02 and 01, but again, the percent difference here is only 0.15%. So now we're looking at the 7th decimal place, and you're getting pretty close to machine epsilon. Clang does roughly the same thing, although it actually inverts. The star is on the bottom here. I forget which algorithm that is. And the cross is up here, and GCC flipped it the other way. That's interesting. Intel did something weird. I don't know what Intel's deal was. It just gave a different answer. So now it's actually more dependent upon which compiler you're using, or rather than which optimizer flag you're using, as to whether or not it changes the answer you get. So this is just for doing the sum once. So I want to see what this is like in a statistical sense. So what I do is I do this 1,000 times, and on each iteration I call std shuffle on the input vector. So now I'm reordering all of my floating point numbers that are not associative under addition. And here's what I get. So the spread in the answer from reordering my input is roughly on the order of the spread in the answer I was getting by changing the optimizer flag. So this is really just reordering inputs is what you're getting, except for Intel. Don't know. So by changing the optimizer flag here, we're really just changing the ordering of input. There's not any arithmetic errors necessarily. It's just the non-associativity of floating point addition. All right, so let's take a look at the other one, and that is code size versus runtime. So we want to look at code bloat. To do this, I look at two different inputs. One is the High Performance Conjugate Gradient benchmark. This is a new benchmark that was introduced a couple of years ago. For those familiar with the HPC world, the old benchmark is LAPACK, which is the old Fortran BLAS linear algebra stuff. That focuses mostly on computation, and so it's really, really easy to get huge LAPACK benchmark numbers by just increasing your IPC a little bit. However, HPCG focuses more on the memory interface, which, as we've seen in previous talks this week, the memory interfaces are not growing as fast as the compute abilities. So this tests an entirely different aspect. And another one involving templates. This is actually a test bench that I wrote for a little SIMD library that I wrote that's based on templates. And a single instantiation of this, a single run of this code instantiates about 200 templates, just kind of give you an idea. Okay, so let's look at some numbers, lots of numbers here. So we have three different compiler options, OS for small, O2, and O3. And you can see that GCC nearly doubles. This is plus 91%, not times 91%. So it nearly doubles in size between OS and O2, and then it adds some more at O3. Clang only adds about 41%, but it was also already about 20% bigger than GCC's output. And Intel is just off the charts. Huge binaries that double in size when you turn on the optimizer flags past OS. The runtimes, you can see GCC is the slowest by quite a bit at OS compared to Clang and Intel. So it's actually kind of impressive. Clang only increased the binary size about 20%, but it was just as fast as Intel's, which was almost twice the size of GCC's. So you never know. And then turning on the other optimizer flags, GCC drops its runtime by about 30% at O3. Clang actually increases its runtime. So at O3, Clang did worse, which is interesting. And then Intel drops ever so slightly. The difference in the final runtime between GCC and Intel at O3 was less than 3%. And yet, the difference in their binary size is about a factor of 1.5. So the space-time trade-off in some of their optimizations are very, very different. You have to be sure to benchmark this stuff. And of course, this is just the text section, so this is just the code essentially that I wrote. and the compiler generated. This doesn't include a lot of library code. Well, it includes the hooks into them. Let's put it that way. So for the template one, GCC generated a fairly small binary, and then turning on the optimizer dropped the size by about 20%. Clang generated a really big binary. It's 5 times bigger, and dropped the size drop is a very strong function of the optimizer here. Intel made an enormous binary that only got bigger when you turned the optimizer on. Yeah, Intel does not like templates. The runtimes for these are in nanoseconds now, not seconds. And GCC's runtime drops by about 40% at 03 compared to OS. Clang drops by about 40% as well, but it's already a factor of 1.5 bigger, so it's still slower. Intel, off the charts in the runtimes. It drops by 85% here, which is a substantial amount, even though its code size grew. But the difference between GCC at 03 and Intel at 03 is still more than 40% slower for the Intel. So if you are using the Intel compiler and you have templates, I'm sorry. Okay. So let's now take a little bit of a look under the hood at what these optimizer flags are actually doing. And I'm going to focus here on GCC because its documentation is the best. Clang and Intel really need to work on that. So by default, Clang and GCC are at 0, but Intel is at 02. And Intel's 02 is a lot stronger than GCC and Clang's 02. So you get a lot of optimizations turned on by default. For GCC, 03 enables all of 02, which enables all of 01, and it turns on the function inliner, so we consider more functions for inlining other than those which were explicitly marked for inlining. And this is enabled at 02 in Clang and Intel, but not until 03 in GCC. The tree loop and SLP vectorizer are not turned on until 03. These are at 02 in Clang and GCC, or Clang and Intel. And unswitch loops gets turned on, which moves your induction variable independent loops outside. So instead of having loop if statement, where that statement does not depend upon I or whatever, it does if statement loop else other loop. And this can be very handy for removing unnecessary branches from your loops, but not turned on until 03 in GCC. Clang and Intel have this on at 02. Redistribution of loops. So GCC will take a loop that looks like this and split it into 2 loops, and then take this first one and replace it with a called a memset. This can be very handy by taking spatial locality and turning it into temporal dislocality, if it can. If you can run this earlier than you run this, you'll have some time savings. There are a few more switches that it turns on, but they play mostly with register scheduling and some of the lower level passes that I don't really want to talk about here today. If you're curious what your compiler is actually doing when you turn on these 02 flags, 02, 03, GCC makes it very, very simple. You just pass in whatever flag you want, a queue, and do help optimizers. If you do help equals target, it'll show you your architecture flags that it's turned on. This is very nice. LLVM is a little bit different. You have some funkiness here, and you pass it into opt with some crazy outputs there. It'll show you what's going on. And Intel has no some such switches. The best you can do in Intel that I have found is you can turn on a flag that will save all of the flags that it turned on into the binary. You do an object dump on the binary and run it through strings, and hopefully you'll see what you want. Yeah. All right. So we've been talking about dragons. Now let's talk about a demon. Fast math. Fast math makes people sweat. Let's see what it's doing in GCC. But a quick quiz. How many think that it's safe to turn on fast math all the time? Every time you run it. By default, it's on. Not a single person. Let this be noted. Talk to the Intel devs. It's on by default. Oops, sorry. All right, GCC's fast math also turns off the error no for math functions that can be replaced with a single instruction. So things like square root. Okay, so it's not always turned off, it's just turned off some of the time. Don't worry about ints and nans, no rounding, no default rounding, although this flag is on by default, so it's not really that big of a deal. No signaling nans. If you're trying to do traps on floating point exceptions, don't turn on fast math. And unsafe math optimizations. This one has a fanciful name. It turns out this is really just a bunch more switches. Sorry, you have a question?
What is math error?
Oh, so in the C libraries, when you call, what is errno? What is this variable right here, essentially? And when you call into C libraries like printf or signf or things like that, there's actually a global variable called error number or errno that gets set to a number. And if that's not 0, then there was an error. Okay, so unsafe math optimizations, what are they doing? So GCC says they allow floating point arithmetic optimizations that A, assume that arguments and results are valid, no ints and nans, and they may violate IEEE or ANSI standards, and they do. For example, it turns off signed zeros. Sometimes this matters and sometimes it doesn't. If you're doing a lot of bitwise comparisons, this matters a lot. No trapping math. We've already seen that fast math already turns off user level exceptions. This just turns more of them off. And in associative math, okay. So here we have floating point addition is not associative. If you turn on associative math, which is weird because it actually turns off the forced associativity properties, it will allow the compiler to rearrange your math computations. Turns out this is very important to be done for certain types of optimization. The other one is reciprocal math. So it takes a statement like A divided by B, and instead of calling the div instruction, it replaces it with A times 1 over B, where 1 over B is replaced with a reciprocal instruction that approximates 1 over B. Note that these reciprocal instructions are only available for floating point, for a single precision floating point, unless you're using AVX 512. The Intel guides for these reciprocal instructions guaranteed 12 bits of accuracy. There are 23 bits in the mantissa, which is about 10 to the minus 5.7, and recall that machine epsilon is 10 to the minus 7. So this can matter if you are sensitive at about 10 to the minus 6. So just be aware of that. And of course, with GCC, you don't have to turn on all of these flags, right? Maybe you just want to turn on associative math, because that's going to help with some of the calculations. And you want to keep, your imps and nans are all checked and things like that. This is just what happens when you throw fast math. Another component to this is the architecture. Oh, short, sorry.
Do you have recommendations on under what circumstances it's useful to turn these things on or off?
Recommendations for turning on these different types of flags, test, right? I can't tell you because I don't know what your code is doing. I don't know how much error you can tolerate. Certain operations have more or less. It depends on precision, things like that. So test. Okay. Another component is architecture. You have to know your architecture. It's so important. It can be hard though, right? Especially for folks who are building pre-built binaries, right? You have some build process that outputs a binary. That binary could run on any architecture. Old SSE machines from 2003, brand new FMA machines like the Skylake that was made last year. If you try to run new instructions on old hardware, you get an illegal instruction exception and your program crashes. So this is actually really hard to do in a generic way. Open source makes this a little bit easier because you can just tell the user to compile it on their local machine. But it turns out this is very, very important. And so it's something that I encourage you to think about. And turning on these architecture flags allows the optimizer and the compiler in general to know more about your instruction set architecture. And all three compilers support SSE, SSE2, for AVX, AVX2, and the newest compilers that I'm testing here support FMA3, 4, and AVX 512. Although I don't have any AVX 512 hardware, so I couldn't test that. Sure, question?
Just in case you know the answer to this, if we're compiling to run in a Docker container on some, I don't even
So if you're compiling for a VM, essentially, some virtualized thing, it can be difficult to know exactly what hardware you're going to run on, right? Because you could get an operating system environment that looks like Linux, but you're really running on Spark. So like I said, it's hard because you really have to know what the physical underlying hardware is. And if you specify the arch equals native, you're going to get whatever this machine really is. So if you're running in some virtual thing that looks like Linux, but it's actually Spark, you're going to get Spark instructions. Okay, so you have to really know, you have to know your architecture before you can start throwing these flags willy-nilly. But they help so much. In fact, there were a couple of really nice talks this week on this stuff, and I encourage you to go watch the videos, or if you haven't seen them. Okay, so GCC offers a really neat little loop, or rather, optimizer flag for loop distribution. I don't know if the other compilers do this. I couldn't find documentation on it. But what it does is it takes a loop that contains two independent statements. There's no data dependency here, no data dependency. This is key. It splits them into two different loops. This can increase instruction level parallelism, and it also turns spatial locality into temporal dislocality because it can run these loops at different times now, assuming it can, present these, assuming that the operands are ready and can be presented without any troubles. But it offers a lot more flexibility in what the CPU can do. Unroll loops. This is an interesting one. It statically unrolls loops where it can. If it can make some sort of an educated guess about your loop induction variables, it'll try to unroll them. This is a huge space-time trade-off, right? Because you're replicating code inside of your loop, but in the hopes that you increase CPU-level parallelism. It's on by default in Intel and turned on in O2 and Clang. You have to throw funroll loops in GCC to make it happen. Clang really loves unrolling loops. I have seen it unroll loops 64 times because it knew the trip count was a const expr. And so it knew exactly how many times that loop was going to go. And it just unrolled it. It was crazy. Strict aliasing. There's a lot of fun in this. This is on at O2 and GCC, and it's enabled by default in Clang and Intel. So be wary of that. So if your code does rely on undefined behavior, even at O2 and by default in these other compilers, you could run into trouble, undefined behavior, pretty quickly. If you violate strict aliasing, let's put it that way. Okay, so let's look at a more detailed example. And this is the famous SAXPY, which is a single precision AX plus Y linear transformation from the old BLAST routines. We're going to look at 33 million single precision floating point numbers. That's about 130 megabytes worth of data, which is much, much larger than any of the caches that are available on these machines. We're going to test three algorithms using expression templates, where the back end is either stood transform, a C-style operator star, operator bracket on T star, or some AVX intrinsics that I wrote myself. We're going to use lots of combinations of switches, O2, O3, and O3 with fast math. I don't put O2 and fast math together because in GCC it doesn't make sense to do that because the tree vectorizer is not turned on until O3. So I just didn't do that one. Looking at two architectures, by default in GCC and I believe in Clang, I'm not sure about Intel, the default architecture you get is this bland x86 64, assuming that you are running on 64-bit compiler. If you live in a 32-bit world, I'm sorry. But in HPC, we don't live in 32-bit world. It's all 64-bit. And the native flag, which says, whatever the hardware really is, give me that. And because I'm running these on my local machines, I know exactly what these are. Of course, if you go to the GCC docs, there are, I think it's something like 30 or 40 different architectures that they support. So native is just one of them. There's a whole list of them. I'm not sure like if the names change between Clang and Intel. They probably do, but they don't have docs on that. So native is what I use. Your use case will probably vary over mine. All right, we're going to look at two machines. My Core i7, Skylake, this laptop right here. It's a dual core with hyperthreading, came out last year. And an AMD 8350 Bulldozer, 8-core machine that came out in 2012. Okay. And I'm only using one thread, even though both of these have parallelism available. I didn't want to test that. One thing at a time. All right, before we get into this too far, I need to make sure everyone's on the same page. So we're going to do a quick refresher on nomenclature of SIMD instructions. So the V here indicates that it's an AVX instruction. If there's no V, then it's some sort of SSE instruction. Then you can add things like add, subtract, multiply, divide, all of your basic arithmetics. And P or S means packed, which means we're doing lots of things at once. And S is scalar, meaning we're only doing one thing at once. And S and D are single and double precision. The move instructions have the V, but they also have a U and an A for aligned and unaligned, unaligned and aligned respectively. And then they do the packed and scalar and single and double precision. So for example, if you see add SS, this is an SSE instruction that adds one scalar single precision float. I mean, it adds two of them together, but it only does one float at a time. If this S were a P, it would be doing 4 at a time or 8 at a time, depending on which instructions that you're using. The V, so this is an AVX instruction, V move APD. So this is moving aligned packed doubles. Okay. This is either storing or loading, same instruction for both. And then the FMA instructions start with V and then FM for fuse multiply. This is doing an addition. There's also a fuse multiply subtraction, which is very interesting. The 1, 2, 3, you get permutations of the 3 input registers. So folks who are familiar with FMA know that this is FMA 3 rather than AMD's FMA 4, which offered up 4 operands at once so that you could store the output to a different register than one of the inputs. Intel said they didn't like that, and so it got changed. These are packed, so we're doing lots at a time, and single precision. So this is just kind of getting you accustomed to this. We are going to look at some assembly code. And so these are the good things. You want this to be a P, not an S. If you are on an AVX machine, you want that to be a V and not a V. Okay. And FMA is great. It's not IEEE compliant because so this does some constant times an X plus a Y, which sounds a lot like the SAXPY stuff we were looking at. And so the multiplication between the A and the X and the addition between that quantity and Y, there's only one rounding that's done. IEEE technically requires 2 roundings, one for the multiplication, one for the addition. You actually get more precision out of this than you do with 2 roundings, but it's still technically not IEEE compliant. And so in GCC, you have to throw some flags to make this happen because it won't do things like this that aren't IEEE strictly compliant. Sure.
You said you want to see the V for AVX. Is that because it's wider or faster?
Oh, so we want to see the question is, why do we want to see the V for AVX? And that's because if it's not a V, then it's not an AVX instruction. Now, I'm sorry?
Well, why is AVX good?
So why is AVX good? Well, if you have an AVX capable CPU, you want to be doing the 256-bit wide instructions if you can, right? So you want to use the biggest lanes that you can, except sometimes not. For example, a counterexample is on Pile Driver. I think the first generation of Pile Driver from AMD. If you tried to use more than 2 AVX loads and stores at a time, performance dropped by about a factor of 10 because their hardware, they had some bugs in their hardware, essentially. But generally, you want to use the biggest lanes that you can, the widest instructions that are available. Obviously, there are counterexamples to this, one I just gave, but if you're doing some weirdness where you really want to do only 128 bits at a time, there are AVX instructions for operating on SSE stuff, but that goes down the rabbit hole. But in general, you want these Vs to be there if you are on an AVX capable machine. And again, knowing your architecture is important, right? So if you throw an AVX flag in your compiler, but you run this on a machine that doesn't have AVX instructions available, you're going to get illegal instruction exceptions and your program's going to crash. All right. So here it is. Here's our SAXPY operation, single precision AX plus Y. Our 3 different algorithms to transform a C style with operator bracket on T star and my intrinsics that I wrote. The runtime in milliseconds. The solid lines are for the Skylake CPU and the dashed are for the Bulldozer. And then the 3 compilers are colorized. And of course, GCC had to ruin my slide. GCC, what have you done? What's going on here? The runtime up here is 100 milliseconds compared to the average for Clang and Intel down here around 30. It's also that for the C style, but the intrinsics doesn't have that. Let's take a look at what's going on. So if I look at only the O2 flag here, so this is looking at all possible flags, the different architecture flags, the different optimization flags. The average runtime is here. This is the maximum runtime and the minimum runtime. So if I just look at the O flags, so O2, O3, and O3 with fast math, we can see that going from O2 to O3, GCC behaves itself much better and looks like everyone else. This is just for stood transform as well. So this is just one algorithm. But then there's still some wiggle room in here because the architecture flag, as we'll see, also makes a lot of difference. So although you can see on Bulldozer, it doesn't do this. And you can see that here too, right? On the Bulldozer architecture, they all 3 look the same. GCC doesn't go crazy. But here, we can see this again, right? So let's take a look and see what is actually going on. So on Skylake, GCC made this. And if you're familiar with assembly and SIMD and all that good stuff, you immediately want to find the person who wrote this in the optimizer and strangle them. Let's take a look. So this is a move SS. So this is loading. So we're moving from memory into a register. A scalar, so 1 single precision float. That's not good. It's coming from the instruction pointer, which means it's moving off the stack. Turns out this is the A and the AX plus Y. So we're moving a constant into the register. We're going to multiply a 1 single precision floating point number from a memory address into that same register. We're going to add 1 floating point number from memory into that register. So this is our AX plus Y. And then we're going to store that register into memory, but only 1 float at a time. It's using XMM0 exclusively for every single operation. This is terrible. You're doing 1 float on something that could be doing 8 floats. Well, note that the V is missing, so these are actually SSE instructions, so they can only do it on 4 floats. But it's doing a memory load every single time into the same register, which means that there's a data dependency between every single one of these instructions. They have to be executed serially. There's no instruction level parallelism here at all. The prefetcher can kind of do a little bit here, but not much. This is terrible code. Terrible, terrible, terrible. And on Skylake, it's 3 times slower than if it had been using packed instructions here. This is very bad. Let's see what Clang did. Clang is using aligned, packed, single precision. Oh, sure.
The question is, wouldn't there would be registered renaming for the vectors?
So the question was register renaming, and yes, the CPU, so the question is, there will be register renaming, will the CPU do it? And the answer is, Skylake doesn't like to do it here because of constraints on the multiply and add ports. Come talk to me later. We can ferret down that hole too. All right, let's take a look at Clang. It's using packed instructions here, great. It's still loading up the constant from the stack, but it's putting it into a register by itself. Okay, and then it's doing packed loads of x and y, then it's doing packed multiply of a times x, and then adding that quantity to y. So the ax plus y here is now being done in 2 different registers. So now we can do our loads at the same time. There is a data dependency here, but there has to be. but we stored away the constant in a register, so we don't have to reload it on every trip through the loop. This is good. And then it just does the store. And then you can see that it's done this again, so it's unrolled the loop twice, and so we're looking at a different load address here, but it's still into XMM1, XMM2. We're still using the same registers. And here, the CPU could do register renaming, so it could rename XMM1 in this instruction to, say, 3, and 2 to 4, and so now it could do both of these loop iterations at the same time. So this is a possibility, and I believe it does, because you saw that the runtime for Clang is way down here, right? So there's a lot more performance happening on structural level parallelism happening in here. See what Intel did. So it loads the constant into register 0, but it does it in a weird way, so I didn't show that because I didn't want to confuse anyone. So we're doing loads into separate registers. The constant is in register 0, so we're doing our AX plus Y in the store. Here, it has renamed the registers for us. It's not relying on the CPU to do register renaming. And so by doing this, it has actually built in something. Well, actually, does anyone know what this is called? By manually renaming these registers and not relying on the CPU to do it? So, I'm sorry? Yes, indeed. It is software pipelining. And only the Intel compiler did this at 02. It turns out this is very, very useful, and the CPU enjoyed it very much. Because you can see that the runtimes were even smaller on the average than in Clang. Okay, so the Skylake CPU really, really liked that. Oh, I should mention that all of the ASM we're looking at was running essentially on both architectures at the same time. So you can see that the bulldozer wasn't sensitive to GCC's silliness of doing one scalar float at a time, with no instruction level parallelism. It actually was able to figure out that it could rename the registers. It could do things in parallel. Skylake, not so much. Okay, and if you turn on some flags, then all 3 compilers essentially generate the same code. It's a packed load into one register for X, a packed load of, a packed load into a different register for Y. The constant was put somewhere else. And then we're gonna do our notice these are AVX instructions. We're gonna do our AVX FMA add, whatever, packed, and now we can do a single instruction does A times X plus Y. This is great. And then we store it back out. And so we're using different registers along the way, although there's a memory operand here for Y. That's fine. This is gonna come straight out of the cache. And so, and all 3 compilers unrolled the loop a little bit here, and so they had several copies of these, and some of them did software pipelining and some of them didn't. But when all 3 of them did this, you could see that the runtimes are, actually GCC is a little bit ahead here in std transform whenever it did that. So I think it was because it turned on more prefetching than the other compilers did. So when you turn on enough flags, GCC does the right thing. It doesn't make stupid code that ran very poorly on Skylake, and then it's actually a little bit better than Intel at its best. So that's for std transform, and the C style with operator bracket on T star, and the intrinsics here. Well, we'll talk about those intrinsics in a second. And so by removing GCC's silliness at 02, the comparison is much better. And so the compilers are looking more and more similar. Short question.
As far as the unaligned versus the aligned instruction, what is that?
So the question is unaligned versus aligned memory loads and stores. It turns out that Bulldozer is hugely sensitive to this because it's a 4-year-old architecture. Skylake didn't really care. And that's generally the case, is that both Intel and AMD have started building chips where they are very insensitive to aligned memory accesses versus unaligned. And the reason for that is because people didn't used to use aligned memory access instructions, because if your data weren't actually aligned and you did an aligned instruction on it, that's a segfault and your program crashes. So people tended to only use unaligned accesses, And so the CPU manufacturers made them nearly as fast as aligned. There are pathological cases where you can show that aligned memory accesses are better. But in general, the newer CPUs don't care as much. Okay, so this is absolute runtimes. Let's take a look at relative runtimes. So now we have just fractions of runtime compared to GCC at stood transform using 03, and that's the only flag. So at this 1.0 point right here is GCC on stood transform using only 03. Okay? So you can see that by turning on other flags, like the architecture flag, for example, we'll see in a second, GCC can reduce its runtime performance by almost 20%. Clang can either be a little bit slower or about 20% faster, and Intel is generally about 10 to 12% faster across the board. Intel is far less sensitive to flags because all of the defaults in Intel are to have these flags on. So it's unsurprising that there's little room in Intel's compiler for getting faster code. And on Bulldozer, things look a little different. So GCC doesn't do as well on Bulldozer as it does even on Skylake. It's very interesting. And Clang is just monstrous here. It's obliterating everybody. It's 10% faster than everybody, and even Intel. The interesting thing here I forgot to mention is, look, Clang and GCC are faster than Intel on Intel architecture. Flags matter a lot, okay? So they can be 10% slower, or they can be about 2 or 3% faster. Flags, it's the only difference. Looking at the C-style stuff, which is operator bracket on float star, things are pretty much across the board same. But notice that there's a lot less variance here than there is here. So when you're using stood transform with iterators, that's a very nice high-level abstract bit of code. But if you don't turn on these flags, you can get crummy output. Whereas if you're using operator bracket on T star, you always kind of get the same thing. But who wants to use operator bracket on T star? That's terrible code. Don't write that. So if we're going to encourage C++ programmers to write nice abstract code, we need to encourage them to turn on their compiler flags so that the compiler sees through the abstraction and goes down to the bare metal. You can't do that without these flags. All right, let's talk about intrinsics. So the intrinsics that I wrote were, I don't know if anyone's ever used them before, they're just essentially little function wrappers around single assembly instructions. And I did the SAXPY, I unrolled the loop twice, so there should be some instruction level parallelism in there. I did some prefetching on the loads and stuff. But it turns out the biggest difference, and of course I used FMA to do the AX plus Y on AVX. But it turns out that the reason that there's a 30% speed up here, 30% on Skylake, as compared to the best that GCC, Clang, and Intel can do using really either one of these methods, is 2 letters in one instruction. It changes here, it changes a V move A PS, which is an AVX load or store of packed single precision. It turns that aligned packed single precision. It turns that A into an NT. And if anyone knows what non-temporal loads and stores are, you'll know why it's a lot faster. I tried as hard as I could. I threw something like 20 flags at GCC to try and get it to do these non-temporal stores, and it wouldn't. And I went searching through the internet, and this is a general problem. The compilers are very, very reluctant to generate these non-temporal loads and stores because they can have nasty side effects if not used carefully. For example, you need memory fences around them to make sure that you get load ordering. C++'s as-if rule must be upheld, and to do that on x86, you need memory fences to make that happen. And so compilers don't like to do that. Intel actually does have a flag where you can say, give me streaming stores. So these non-temporal loads and stores are also sometimes called streaming loads and stores. And there's a flag that says, give me streaming loads and stores. I didn't use that, but That's the only difference, is you take an A in a load, which is an aligned load, and you turn it, or sorry, a store, take an aligned store and turn it into a non-temporal store, and 30% speed up. Now, the really, really frustrating thing is that I went and wrote code. So I wrote this algorithm back out in C, which is everyone's favorite language, right? Compiled it under GCC 6.2 with the C language, gave me non-temporal loads and stores. So I'm not sure if it's because of C++'s as-if rule, where GCC doesn't want to give me these non-temporal loads and stores, or if it's just a missed optimization pass. I don't know. I plan on filing bug reports. I didn't test this on Intel, but Clang didn't do it either. So I may be filing some bug reports. Okay, so that bit of sadness aside, this is what we're looking at. So the interesting thing is, so these are across the algorithms. The interesting thing is the spread in the amount of speed up that you get based on different flags, right? So here we go. That's the answer. Do compiler flags matter? Yes. When do they matter? Depends. How much performance speed up can you get? It depends. And so when I look at this plot, it actually fills me with a little bit of happiness, because you know those people who say, oh, don't use O3, it's terrible, you won't get speed ups versus this and that, don't use fast math, you know, things like that. Oh, I know that if you throw this flag, this is going to happen. I know. Well, no, you don't. You don't know anything. And you can't know anything about what's going to happen unless you benchmark it. Okay? I was surprised by some of these results. But this is the necessity of benchmarking all of this stuff. So quickly, so I threw out GCC's O2 thing because it was silly. And so we're looking here at O2, just the rest of them. Every point in here, so for the solid lines, every point is measured with GCC at O3. So the 1.0 here is the normalization for both architectures, although separately. So at O2, the compilers actually run faster than GCC at O3 by itself, which I thought was interesting. But if you throw the architecture flag at O2, they go from about 5% faster to almost 15 to 20% faster. GCC is a little bit weird here, but look at Clang. It goes from 5% faster to 15% faster. All I did was throw an architecture flag, O2 and architecture. But if you just do O3, well, the numbers are kind of the same everywhere, right? Except that Clang actually gets a little slower, which was interesting. I found that to be sort of the case, is that Clang doesn't like O3 very much. But from what I could tell, it only throws one additional flag. I don't know, maybe there's some internal algorithmic stuff going on. O3 in architecture gets us back down here. And in fact, GCC loves O3 and the architecture flag. Look how much faster it is compared to O2 in the architecture flag. So big speed ups there. O3 was fast math, very little speed up. You can see Intel is actually quite consistent across here because it already had the fast math flag thrown because it's on by default. But between O3 and O3 with fast math, Clang and GCC don't really change. And then this is both across both architectures. And then O3, fast math, and the architecture flag, Bulldozer gets slower. That's interesting. All three compilers get slower. But look what happens on Skylake. GCC is almost 5 times faster than Intel, and Clang is only just a little bit slower than Intel. So when people say, oh, GCC's optimizer isn't that great, you know, sometimes it does okay, sometimes it does poorly, I said, well, that's because you didn't throw enough flags. So you got to throw lots and lots of flags to get GCC to do things, but when you do, well, on Skylake, it's super great. On Bulldozer, not so much. So you have to know your architecture as well. Okay, and that's all I had. So here are some talks, just a second. So here are some talks from previous conferences that are great. If you have any interest in this type of stuff, These are great talks. And these last two here are from this year. John Ferrier's talk on floating point arithmetic is just, it was mind-opening even for me, and I come from a computer science, well, everyone here probably comes from a computer science background as well. Sorry, I'm accustomed to talking to astronomers, and they don't know anything about computer science. So it was great. It was great. His talk was great. Okay, so any questions in general? Sure, question.
Go back to the previous slide with the graph. Am I reading that right, that Clang got slower with fast math?
So the question was, did Clang get slower with fast math? You're talking about O3 fast?
Between O3 plus Arch, the blue line is at 1, or is at A5, and O3 plus Arch plus fast math.
Yes.
It got slower.
Yeah, it did. So Clang at O3 and the architecture flag versus Clang at O3, the architecture flag, and fast math, it got slower. Fast math didn't help. It didn't help Clang. It actually hurt, but it helped GCC and Intel. Although interestingly, Intel produces its fastest code at O2 in the architecture flag. I thought that was interesting. But even though fast math is on by default, I don't know. I didn't have an answer for that. That was interesting. Sure.
Is using O3 in previous versions of GCC a good idea?
So is using O3 in previous versions of GCC a good idea? The only answer I have to that is you'll have to test. I only use 6.2 here because it's the latest and greatest. If you're stuck on 4.1 or something like that, you really want to test. I can't make any guarantees. Sure.
How statistically sound are those measurements?
So how statistically sound are these measurements? Not terribly. They're single runs. So if they're single runs of thousands of iterations. Does that make sense? So each run is thousands of iterations and then averaged together, but they're still only single runs. So if there's noise in the system, I do actually have some error bars in here, but I didn't want to put them on there because there's already enough points on there. Sure.
Do you have any idea why the bulldozer and Skylake seem to be reversed in performance for Clang?
So the question is, why is it that Bulldozer and Skylake are reversed in performance for Clang? For example, at O3, the Bulldozer numbers, there's about 10% speed up for Clang, but on Skylake, there's about a 2% slowdown. And the answer to that is, I have no idea. It's sensitive to the underlying architecture. The code that it happened to produce was good for that architecture and bad for Skylake. Sorry, yes?
Yeah, I've got a huge customer base, and I'd love to raise the bar on minimum architecture, but I just can't do that for all the customers. Are you aware of any software packages that emulate?
Oh boy.
So that I can say, okay, if you care, buy this hardware, but if you don't care, you can get emulated and it'll be slower, but it'll work. It won't crash.
So the question is essentially, how do I support multiple architectures, with these flags, right?
Yeah.
And the answer to that is, well, there was actually a really neat company about a decade or so ago called Transmeta that were going to try and do this in hardware. They went bankrupt. Doing it in software is hard. You either have to compile all of your translation units under different flags and then link them together into different binaries. You can try and do some runtime detection of these things and then load or call different functions and hope that you never accidentally run into illegal instructions. You can try doing runtime module loading. There's not a really good answer for how to do multiple architectures. It's important, but it's also really hard to do in a generic way. Sure.
I'm particularly interested in the spread between the maximum and the minimum.
Sure, in here.
So, did you prove any of the results? And were you able to determine the maximum was the first time that you executed the algorithm? Or how did that distribute over time?
Oh, sure. So the question is about the spread in the results here. And the first question was, did I prune any results? Yes, one, where GCC was stupid. Did I, sorry, what was there was something about.
So the spread was the maximum the first time that you executed the algorithm, and then once it warmed up, the branch predictor or anything?
So the question is, essentially, did I warm up the caches and things like that? Yes, I do a priming run on the caches. and then I run it for 1,000 times. And then I take the average. So this point right here is actually an average over 1,000 iterations of the same algorithm. And so remember, there's 130 megabytes of data sitting behind this. So all the caches are going to get poisoned along the way.
I understand, but imagine this. Like, this is what you calculated as your average, right? You maxed it in here. So did it store the average?
Oh.
Did you get a maximum at the end?
So no, I did not look at the statistical distribution of the 1,000 iterations, essentially. Like I said, I do have error bars for these points, but I didn't put them on here because it's already noisy enough. But yeah, I do have error bars, and on the average, they're on the order of about half a millisecond, plus or minus, where you're looking at roughly 25 milliseconds on Skylake, plus or minus half a millisecond, and 50 milliseconds plus or minus half a millisecond on Bulldozer. So the spread in there is not very big, but I didn't check to see if it was actually converging down to a single answer or not. That is a good point and something you may want to look at when you're doing microbenchmarking. Okay, sorry, that's all the time we have. So if you have other questions, let me know.